classes and in my group is actually teaching people how to work in teams. And so we're going to do these hands-on exercises today, and today it's almost all of them hands-on exercises. So in the morning it will be PDF Get X3, and in the afternoon it will be PDF GUI. So we'll do mostly hands-on today, so you'll start being able to do some projects on your own. But I wanted to have you do this in teams. So one question is, why is a team better? And actually what the research suggests that if you have people with a diversity of ideas and also a diversity of personalities, and you can make them effectively work together, you get actually better solutions and you get more productivity. But the key aspect of it is this diversity. So if you form a team which is a group of people, and the group of people doesn't operate like a team, then you failed. So in other words, if you put 4 people together and you call it a team, but there's one person there who has a very strong personality, and they push the other people aside and say, I'm better at this than you, I'll do it, you've failed. You haven't made an effective team. And that group of people may produce some product, but it won't be as good or as quick as the teams that are operating effectively. So it's actually important to learn how to work in teams, and it's not how we normally operate, and it actually takes a little bit of effort to do it right. So what we do is we set up a little bit of a structure for the team. So the first thing is I have a program that randomizes a list of people and places them in teams. I wrote the program in Python. So what I can do is run the program, and that will form your teams. So it means that I'm using randomness to get diversity. So the teams are not all friends who are close together and all the same gender and things like that. Some of the teams will be all the same gender just because there's not enough genders. There's only 2 genders. But this randomizer will put you with people who you're not used to working with, and you have to learn how to work with those people. Now, it turns out that there's different roles that you can play in the team. Okay, and so I'm going to make you into teams of 4 people. And the teams, that means there are 4 roles. So you're a person, but when you join the team, you have a role. And the 4 roles are, actually I don't have a view graph on this, so I can type them. So there's the team leader. Oh, it's not very good. This doesn't go wider. Actually, let me... Okay, so one person in the team we call a leader, the team leader. Now, you might think that the leader has to be very strong and tell everyone else what to do. But that's not the role of the leader. The role of the leader is to ensure that the team is a successful team. And for a team to be a successful team, it means that everyone in the team is contributing. And that's because you want to make use of all of that diversity. So when you discuss things and you make decisions, you want to reach consensus. It means that you want everyone to say what they think, and you want everyone to be heard. But after everyone's been heard, you want to discuss what was said, and then come up with some consensus opinion. So the consensus doesn't mean everyone agrees. If everyone agreed, it would probably be a bad team, because there wouldn't be enough diversity on the team. So the consensus means that everyone is happy with this kind of compromise situation, and no one is feeling like they weren't heard. So the leader's role is to make sure that everyone has a voice and everyone is heard. That's really what the leader does. The leader is also in charge of making sure that the team delivers. So you have some objective you're trying to deliver, and there's some time scale that you have to deliver it on. And if people are talking too much, but the discussion is not coming to any kind of consensus, the leader has to very gently bring the discussions. They have to say, we're running short of time, we need to reach a consensus before the tea break, blah, 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 something. So that's the leader. In my groups, I also have a scribe. So scribe is somebody who records things, they write. So depending on what the project is, you may be writing a document, or you may be writing notes of what the discussions were. And in some of these hands-on exercises, maybe the scribe is the person who's typing at the computer, so the discussion will be, what should we do next? There's a discussion, we should try this, and then there's some questions, why did you do that? And then they say, okay, let's have the scribe try it, something like that. So you're not all sitting on your own computer, you're all sitting around a single computer, and you're discussing what to do, and then you're doing it together. So the scribe is the person who writes things and records. And another role, I call it optimist. So the optimist is the person who's very confident. They think everything will work. And they say, I know what we should do. Let's try and cure malaria. That's a really big problem. I think we can do it. So you want someone who's very positive. They're bringing positive energy to the situation. Everyone is a little bit depressed because you've found some problem you can't solve, and the optimist is bringing energy and saying, yes, we can solve it. And then you have the fourth person is a skeptic. So the skeptic is actually the depressed person who thinks that nothing will ever work. So they say, so what's the role of the skeptic? Why would you want a skeptic on your team? Because, the skeptic is actually going to bring some realism. They're going to say, it would be nice to cure malaria, but we're only 4 people and we have no money. It's maybe we should think of something not so ambitious, and so it's important to have, again, these kind of diversities of points of view. So what I've done now, when you're in a real team, sometimes these things form naturally. There's a lot of misunderstanding about the leader. So sometimes you'll self-select. Like if you're a naturally optimistic, positive person, then you're likely to be the optimist. If you're a naturally kind of skeptical person, you'll be the skeptic. The way that things go wrong is that the people who think that they're natural leaders, typically in the US we call them A-types. They have an A-type personality, which is a very strong, overbearing personality. And these people actually make the worst leaders in the context of a group like this. So in order to not have you have to discuss with each other what your personality is and decide it's awkward, right? Who's going to be leader, who's going to be this. So my program tells you who's going to be what. So I'm going to run my program. It's going to put you all into groups. Now it's using the list that Atul gave me. And I'm pretty sure that there's more people on that list than there are in this room. So what we'll do is I'll run the program and we'll form into the groups. And I think some of the groups will not have enough people. After we form the groups, we'll figure out which ones have not enough people and then we'll redistribute the people so we have all groups of 4. Does that make sense? So according to the list, there's something like 12 groups. So we just need 12 locations in the room. And the groups are numbered 1 through 12. So I think we should do this. We'll do group 1, we'll go over there. So if you're in group 1, you go over there. And if you're in group 2, you go there. And then group 3, and then 4, and then 5. And maybe in the first 2 rows. So when you work in a group, you actually want to be in a circle, kind of. So the best thing might be, do these chairs turn around or not? They're fixed. Yeah. So we're going to have to, that's an early challenge for your team that you're going to have to solve, is how to effectively kind of work together. But we'll have 1, 2, 3, 4, 5, and then in the back rows 6, 7, 8, and then let's just do it over there for now, 9, 10. Wait, 1, 2, 3, 4, 5, 6, 7, 8. Oh, we have that corner, yeah. Okay, 1, 2, 3, 4, 5, 6, 7, 8. What? 8, 9, 10, 11, 12. Yeah. Okay. Is everybody ready? Oh no, there's 14 groups. Okay, so all I can show is this many groups to begin with. So if you're in one of these groups, that's a good idea. Yeah.
But they can reach to their places so that we can see.
Yeah, so Atul, you're a born leader.
So I don't have to be very big.
Yeah. You weren't on the list. So some people actually won't be on the list. We'll add you to groups. Okay, so if your name, yeah, so note down your group number. Has everyone found their name who's there? Okay, I'm going to scroll it down now. Look, Sophie Billinge is in group 10. Sophie, you bring diversity. Okay, has anyone not seen their name? Okay. So if you didn't see your name, come down here. So you guys from Varanasi, right? Yeah. So maybe you weren't in this version of the list because you came late. Come down here. Yeah. Okay, so you can form up. So group 1, 2, 3, 4. There's no 14. I only did 12. Okay, this is 13, 14. Your name's not there. Yeah.
Pragya Singh. Pragya Singh.
Like, I think some of the people will be absent and will be reached out
So some persons in this list are missing.
Yeah, that's fine. That's why.
Do the substitutions.
Yeah, but if the groups form up, then I mean, a fresh list is obviously better. Yeah.
That's all the people who are there. Simon, just make the substitutions in the
Yeah.
groups that you have already made.
Yeah.
Because the fresh
Well-
list is also not reliable. Take your position.
Yeah. If you're in group one, then even if it's only one person, group one, yeah, get two. Group two. So I think, yeah, so group two, join these.
Group 3 is here.
Group three is here.
And 4. Group 4 is anyone from 4 to
Group four is here.
Group 5.
So if you don't have, if your name is not on the list, then come over here. So group 5 is here.
Group 5. Anyone from Group 5?
Yeah,
Group 6.
you're over there. Your name is over there.
Group 6.
The 6 is over there.
Group 6.
Group 6 is the one that's behind. Next row back.
Okay, second.
Third row. Third row.
Group 6 is in 3rd row. Group 7.
Yeah, group 6 is here.
7 also in 3rd row.
Group 7 is here in the middle.
Go ahead. And group 8.
Group 8 is here.
Okay. Harpreet, आपका कौन सा group?
14 number.
So you are with Krishna.
14.
Yeah. So group 9 is over there.
9 is Krishna.
9 is here, and then 10 is here. 10. Okay, yeah. Okay, yeah.
10 is
Group
here.
10, group 10 is here.
You are in that? No. You know media very well.
Yeah.
11. 11, any only one. Okay, we will add some. Any more? Second. 5 is here.
Okay.
11. You are 11.
Yeah.
So
You're 11?
No, I'm 12.
12. So 12 should go to the back. Yeah.
Yes, we 3 are in 12.
12 you go behind them.
11 and 12 get 12.
आप इधर आ जाओ.
And you're 14 or 14? 14. So that's Skeptic. It's fine, yeah. So, and then 13. Is anyone in 13?
That was बता दो. 13 anyone?
14 and 12.
13 is
You're 13. Okay, so just go to the back there. So if your name is not on the list, please come here. Okay, so we're going to start to making the groups whole. So why don't you join group 1? And your role is whichever Mrs. Rift is Mrs. Okay, so you join 2. Now 3. Okay. This group, sorry. Okay, so you join 9. 9. Yeah, okay, so yeah, you join 9. Which number are you? 7. 7. Okay, you join 7. Okay, and then you join. What are you? Are you complete?
11.
11. 11 is complete.
No, you are all 11. You are in 12. He is in 11.
In 12, we are only 3. We can get merged to form one
Okay.
group.
Yeah. Now come down to your group.
You come.
Okay, you join group 12. Okay. So now we have 2. What's your group number? 8. 6. Okay, why don't you join 6? You have 2, right? Yeah, why don't you join 8?
Shiva.
You have 3. So why don't you join 7?
13.
Now you're 1. Yeah. You have 4. Yeah. You don't. So they have 3. 6. Group 6 has 3, right? Yeah. This is perfect. Okay. So can you join group 6, please? No. Oh no, it's not you. It's, okay. So could you join group 6?
You are in 13. You are 39. Please take your seats.
Okay, so everyone should be in a group, and every group should be full now, I think. Is that true? Now the groups need to spread out a little bit. So you guys in the middle, yeah, you already moved. Yeah, so you guys can move, and you can move the seats at the back. And like I said, it's actually easier if you're not all in a row. But it's hard with the chairs. So figure out for yourselves. So you guys move 1 row back. Yeah, so you're more spread out. Yeah. Okay, and maybe you guys move down that way so that you're giving people more room. Yeah. So move to the other end.
Group 1 is here. 2. 3. Group 3 is 15. You are in 3.
No. Then everyone's set now. Everyone. So everyone, you should know you should know your group number and you should know your role. Now, the first thing you should do in that pen. Okay, so now you're a group and you want to turn yourself into a team. So one of you is the leader, so the leader should probably take control. And it's very important, as I said, that everyone's voice is heard. So it's very important that everyone in the group knows who everyone else is in the group. So the leader should reach out to people in the group and ask them what their name is and ask them to introduce themselves. And it's actually very difficult for me when I'm with Indian people because I'm not used to your names. So it might be also helpful just to make sure that everyone knows who everyone is if the leader asks the scribe to write down everyone's name. And so you have this list of names. And just all say hello to each other and get to know each other for a few minutes. Okay, go. You're allowed to talk now.
She's the leader.
Yeah.
I'm the skeptic.
You're the skeptic.
He's the optimist. She's the scribe.
Right. And you know all each other's names, so yeah. And how are you going to refer to Honourable Professor, senior guy? He's part of your team. Are you going to call him Honourable Important Professor?
What are the such thing?
Yeah.
First name basis.
Yeah. So you should ask him. Krishna, sir.
No, sir.
No, because you have to hear his opinion, his voice. So you have to say. So you have to say, sir. How would you like us to refer to him? No, you say to him.
Just refer to me as Mukul, although I'm the leader, we are the group, so just call me Mukul.
But how does he want to be referred to? So you ask him. You ask him. Yes. Yeah.
Siva is skeptic.
Okay. I'll give the upper list. And so those, please try.
Do you know everyone? Yeah. Did you do that? You wrote down the name.
Yeah, one.
Very good.
No, don't worry.
Okay, so you got to know each other and you started to feel, and people should know what to call each other, so that you're all on even level playing field. There's no kind of caste system in a team. If a team has a caste system, it's doomed to failure. So you all have to be comfortable and say, I'm not comfortable being called by my short name. Can you call me my long name? You can say, yes, but just make sure that you're all comfortable. And then what I'm going to do now is I'm going to just show you actually the hands-on demonstration, and then in your teams you're going to start doing hands-on demonstration. So the first one is actually PDF getx3. I'm not going to show you XPDF suite, just PDF getx3. This is the free version, and this one you have to pay for. It has a nice GUI. It's easy to use. If your advisor has spare research funds that they can pay for this, then it's much nicer to use. But for the school, we're just doing this PDF getx3. And so the objective is that you have raw data in the form of a one-dimensional diffraction pattern, and you've collected it from a synchrotron, or you've collected it from a MOLY K-alpha X-ray source in your lab, or from somewhere else. And so the goal of this tutorial is to ensure the software downloaded, installed, and working. So one of the goals is to ensure that it's downloaded, installed, and working. When you're working in your group, what I really want is just one person doing the analysis and the other people suggesting things and posing questions and answering questions. But at the end of the tutorial, I want the thing working on everyone's computer. So one of the goals for your team is to work together to make sure that the software is working on on everyone's computer. Now, we have some people who can help with software installation. So one thing to do in your team is to try and solve as many problems as you can using the expertise in your team. But when you realize that there's not enough expertise in your team, it's appropriate to reach out and say, we need extra help, and so then put your hand up, and I or someone else will come and try and help. Okay, so a good team tries to solve as many problems as they can with their own skills, but a good team also recognizes when it needs to seek outside help, and then it goes and seeks help. Then we're going to set up firstly the config file to do the PDF getX3 analysis, understand how to run the software and get a good PDF from the data, and then we're going to use this thing called tuneconfig. So I'm going to actually demonstrate this up here, and then I'd rather you didn't follow along but actually just listened, and then when I finish, then you try and do it. So the steps go like this. If you go to the 00 underscore PDF getX3 folder in the tutorials, you'll find a file which is called template.cfg, and you want to copy that to a file with a new name. Then you're going to open that in a text editor, and you're going to edit it for your sample. Then to run the program, you just type PDF getX3 -C, which stands for config file. CFG is config. And then the name of the file, so you've changed this to a new name, you type the name of the file, and this is -I for interactive. If necessary, you'll run tuneconfig. When everything is beautiful and you're very excited and happy about it, you type process files, and that will actually write the GFR files onto your disk. And you can exit and look at the data. So this slide is very important. This is actually where the documentation is. So these are actually the links. This is to a web-based documentation. So you can only see this if you're on the web. But there's a PDF copy of the same manual, which is at this link. And I gave you just one file to play with, a nickel file. But if you go onto the web and you go to this website here, there's actually a bunch more examples. There's Syria, there's barium titanate, and there's an organic material. So these are good to go and play with. Now, if you can't, it's a lot of typing to get this without making any typos. So it might be actually easier to go to diffpy.org. That's where all our software is, diffpy.org. And then there's a button that says Products, and you scroll down to PDF getX3, and you'll get the PDF getX3 website. And if you look in that website, you'll find basically these manuals and tutorials. Okay. So I don't think you have internet connection in here, so you can't do that right now, but you can do it later. If you want, you can reform your team later and work on this together as well. Okay, so this is the I think you all have this. So it's tutorials. No, this you don't have. You have this tutorials 00_PDF getx3. So that one was the file that you should have received yesterday. Now, if I do ls, I list what's in that directory. There's a readme.txt, then there's a data directory, and these are, you have this and you have that, but you don't have the PDF getx3 manual, and you don't have the PDF getx3 examples. I downloaded them from the diffpy website. You can download them from the diffpy website later. But I just did this so that I had some more rich examples that I could demo to you. But what you can do in this hands-on demo is you can cd, change directory to data. And if we do, actually on some Windows machines it's dir. Okay, there's a bunch of stuff that I've put in there by accident, but basically you've got anything with any file with a extension chi, chi. This actually contains data. So there can be other file formats, there can be other file extensions that contain data, but this chi file contains data, raw data. So there's a nickel.chi and there's a kapton.chi. Now, when we collected the data, we had powdered nickel, and we put it into a kapton capillary. And as we discussed yesterday, we measured the nickel inside the kapton capillary, and then we measured the kapton with nothing inside it. And so these are the two data files. This is the nickel and the sample container. This is the empty sample container. Any file which has a GR extension is a PDF. And these are all text files. So what I'll do is I'll just show you what they look like. So firstly, we'll look at the nickel.chi file. So it's a text file, so any text editor will read it. And what it has is it has this bunch of metadata in the top. I think maybe I already showed you something like this, right? So it tells you about the experiment. The data were integrated from a 2D detector in QSpace. The X-ray wavelength was 0.1835957. These are calibration parameters for the integration. The data were integrated on a Q grid with a step of 0.02, and it's actually in inverse angstroms. These are things that you don't really need to know about. But this tells you that it's been corrected for polarization. That when it was integrated, that the errors were propagated. So there's various little bits and pieces you don't really need to know about. And then there's start data. And there's actually 3 columns here. And the first column is the Q value. The second column is the intensity. And the third column is the uncertainty on the intensity. And then there's lots of data that goes all the way down. And one way that I know that it was in inverse angstroms is that it ends at around 30. So the last data is 31.26, and there are some zeros at the end. So that's what the data look like. Now, inside PDF getx3 is a program that is kind of very handy for plotting. So it's a text file, so you could use any program to plot it. You could use Origin or whatever you use. but we have a handy, helpful one which is called plot data. So plot data, space, and one of the data files we want to plot. So let's plot the nickel.chi. So this is a matplotlib window, and it's just plotting nickel.chi. So this is the raw intensity, and you can see beautiful Bragg peaks. And it has this nice function for zooming. So let's say that we want to look in the high Q region to see what the data look like. I might want to just enhance that region. So you can see we have these broad Bragg peaks extending out to 25, and then it's looking kind of flat, and then it goes completely down at 30. Okay. Now, I can also, what's happened is that this plot data has put me into an IPython prompt, and there's a way that you can use this program in a more advanced fashion by using the IPython prompt, and that's described in the documentation, but I don't want to do that today, so I'm just going to exit out of there. Now let's look at the background file, so we'll look instead at Kapton. So Kapton is a polymer, and it's an amorphous material, and so it basically has no Bragg peaks. That's what the scattering from Kapton looks like. It has this big broad hump down here at around 1 or 2, and it has some smaller humps here. But it's like, this is why we like using Kapton for a container, because it's kind of fairly weakly scattering, and it's the scattering is very smooth. And it looks like, because the thing was on a full scale, it looks like they both have a similar intensity. So what we can do is we can plot them together. So what we do is we say plot data, and then we list, you can give a space separated list of all of the data that you want to plot. And now you can see it looks like this. So they're both simply plotted on the same plot. And what we can do is we can look down here, so we can zoom in, and we can look at where the intensities. We can expand the low Q region, and the green one is the Kapton, and the blue one is the nickel. And what we can see is actually that we've overcounted the Kapton, so that the Kapton signal in the Kapton data is higher than the Kapton signal in the nickel data. So it means that when we're going to do the corrections, we're going to have to multiply this Kapton correction by some number less than 1. And we can estimate it. We can look at this peak here, and let's say this is 10. So that's about 7. And this is about 16. So it's about 0.4, 0.4, or 0.45. So we're expecting that we'll have to scale the background by a factor of 0.45. And this thing will bring this peak down to here, and it'll show this thing. It's incorrect for this green line to ever be above the blue line. If I press this little house here, it returns it back, and then I want to zoom into the high Q part. And here you can see that the scattering from the Kapton is quite a bit lower than the scattering from the sample, even though we've overcounted the Kapton. So it means that a lot of the scattering out here, even though there's no structure, it's actually coming from the sample itself. So the convenient thing with PDF getx3 is that you can run it with a small number of commands. But what we do then is we put a lot of the information inside a config file. So I have here template.config. So I'm going to open that up. Whoops, I want to open it in a different. So it has lots of lines, and at the beginning of the line are these hashes. Those are comment lines. So there's a lot of information that you can go in here. So there's a parameter here called wavelength, and there's a thing that tells you what wavelength means. So it's X-ray wavelength in angstroms. And it's only actually required if your data are in 2 theta format. So our data were saved in Q quantity, so we don't have to, even if you gave a wavelength, the program wouldn't use it. You can give it, and so actually this has been commented out here. So we have 2 of these hashes if it's actually a comment, and then that allows you to either this one is not commented out, but this one is commented out. You can give it an input file or not. So if there's information that the program needs that's not in the config file, then it will ask you for that information. But we generally put as much as we can in the config file. So actually it's asking if you have a background file. And then it needs to know the composition of your sample. Then it's going to ask you, when you do your analysis, which functions do you want to plot? IQ is the raw data, f of q is the normalized intensity in Q, and g of r is the PDF. It's going to ask you what outputs you want. So when you process the files, it will write files, and you can put a list here. It could also be FQ and G of R if you want to have a file containing the f of q function as well as the file containing the G of R function. Here's a background scale, which right now is 1. This R poly I'm going to tell you about later. This Qmax inst I'm going to tell you about later. Qmin, Qmax I'm going to tell you about later. Now these are for the PDF. So if you give it rmin to 0 and rmax 60, it's going to compute the PDF from 0 to 60. These are good default values. You probably don't want to change them. And 0.01 step size in R is pretty common too. So there's a lot of stuff you don't want to change. But you actually don't want to change the template file because you want to keep it as a template file. So the first thing we want to do is we want to copy so we want to copy template, copy. You can just use your Windows thing to do this too, but we can copy template.cfg to another name. So what should we call it? We'll call it live demo.cfg. A word of advice here is that it's actually much easier for programs. It's easier for humans if your file names have spaces in, but it's easier for programs if your file names don't have spaces in. So if you want to avoid headaches in the future, make a file name without spaces in it. So I'm going to call it live demo, and I'm using a thing that in software programming we call camel case. So you all know what a camel is, right? It's this kind of animal which has a hump in the middle. And you can see that capdon.chi. That was the empty container. Now the composition, this is the because you're subtracting the container away, you don't have to put the composition of your container. So this composition here is the composition of your sample. And a very handy thing in the program is you can just write it as a formula like this. You can also use this format, separating things with spaces, but actually this is always the most convenient. So if I wanted to do barium titanate, I could simply write barium TiO3. If I had a barium titanate sample, I would type that. But I have a nickel sample, so I type that. Okay, now this is telling you what you're going to plot when you actually run the program. And this tells you the output file, and here's the list of possible ones you can have: S of Q, F of Q, G of R, and also I of Q. So I think we might want to do F of Q and G of R. Now I'm not sure if it's space separated or comma separated. Yeah, this plot is comma separated. So I think it's a comma separated list. Now background scale I'm going to leave as 1 for now. I'm going to leave these guys. Actually this one here I want to change. So we had, so it looked like 31 in the file, so I'm changing that to 31. And actually I want it to go into interactive mode, but I'm going to leave that commented out because I'll show you how to do that at the command line. So I'm going to save this. I can close it. Now running the software is actually straightforward. So all I have to do here is I have to do PDF get x3. What it will do is it will automatically go and look for a file called pdfgetx3.config, and it will try and run it. Let's see if there's one in there. Yeah, so I do have one hanging around. So I'm going to actually remove that one. So I could just type pdfgetx3 and it will run, but it won't really know what to do. So I haven't given it an input file, and it doesn't know what to do. So what I could do is I could do pdfgetx3 and give it an input file, which is nickel.chi. And it doesn't have, again, it doesn't have enough information because I haven't given it a config file. So what I do is I say, okay, -c is my config file, and I called it live demo.cfg. So now pdfgetx3 is going to use this config file on this data set to run. So now it has enough information, and it's actually, it's read the data here, it's produced an F of Q, and it's produced a G of R, and it's actually done a fairly good job, even with us not doing anything. So now we're in a command prompt here. So it actually put me into interactive mode. I'm not sure why. Or maybe because I had that plot thing set up. Okay. So what I want to do is actually, it's easier to demonstrate what I want to show you. Remember, we have to do some things like we have to vary Qmax, qmin, some of these parameters, and we want to vary the background scale. We know there's a problem with that. So what I can do is here minus minus plot equals fq gr. So I don't want it to plot I of q now. I've seen that enough. Seen enough. All right, so now these plots are a little bit bigger. Now the next step is kind of the most fun in a way. So what we want to do is you can actually give parameters to the program by typing them into the config file, or you can actually do config, and then these are all the different things that you can configure by actually giving numbers. So you can give config.qmin equals something. You can do config.qmax equals something. But a much better way to do it is to run this little program, tune config. And you have to remember to do these parentheses here. And that pops up this little thing here with sliders. So I don't have much room on my computer here. But here's the f of q that I have, and here's the g of r. And now I can try varying all of these things by just grabbing this with the mouse and moving it. Okay. Now the first one I'm going to do is I'm going to move qmax inst all the way up to the top. And I'm going to move qmax all the way up to the top. And this is somehow what you often see is at the very edge of the data, there's weird stuff. And actually, the reason that we have, so qmax is the maximum q value that the program is going to Fourier transform. But what the program does is it fits a polynomial to the data before and subtracts a polynomial fit before it does the Fourier transform. And qmax inst is the range that it will fit the polynomial over. So there's actually no reason why the program would fit the polynomial over the same range as it Fourier transforms the data. That's why we have two parameters. So qmax inst has to be larger than qmax, but it can be any number. Now, by putting qmax inst up to 31.5, I've got all this bad stuff in here, and my polynomial is going to try and fit that bad stuff. And this can sometimes lead to real problems. If we look at the barium titanate example, we'll see that. So what I want to do is I can go here and I can zoom in, and I can say, look, this is varying nice and smoothly, and it's really varying smoothly up to there. But I could also be more conservative and say, well, that's where it kind of starts behaving badly. Now, if I can find it. So if I put this guy on here, I can click. Actually, I don't think I even have to click. Yeah. So if I select this pan view, I can place my cursor at some place like this. And then if you look down here, it's telling you what the x and the y values are. And so my x value is 30. So I think conservatively I would like to make my qmax inst to be 30. Oops, what happened? I think I accidentally closed it. So I can use the slider here. I can slide my qmax inst. Yeah. So at the command line, when I executed it, so there's two ways to do it. One way is you edit the config file, and you just change it in the config file. But I wanted to show you that actually, so if you always want that same thing, you know, so what you put in the config file is what you want the kind of default behavior to be, but you can modify it at the command line. So I can move this, I want to get it to 30, so I can move this slider to 30. And now if I move my Qmax up to the max, the Qmax will only actually go up to 30. And now what you'll see is that the blue curve here was the original one that we made when we opened the file. And the green curve is the one that we have now. So this was the blue curve, and this is the green curve. And we can look down in the PDF and we can see how it's changed. And what you can see is it actually hasn't changed that much. There are really very tiny changes. Oops. And some of the biggest changes are maybe down here at low R. One thing that's happened is that we've decreased the size of the ripples down here, and that's because we've removed noise. So there's always this trade-off. If you go higher in Q, you have a higher resolution, but you have more noise. And so it was a good trade-off to not put this noisy stuff into the data. Now, our background scale is fit at 1 here, so we can play with the background scale a bit and see what happens. So actually, if we increase the background scale, actually for this one we actually want f of q, I of q plotted. So actually we want, yeah, let's actually just do it with I of q and g of r. Now we can change the background scale. We can increase the background scale. And what you can see here is that in this low, remember that the background had this big peak at the low Q region, and we're subtracting it. So the green curve, which is the new curve, we're over subtracting now. We're subtracting too much. And even before it looked like we'd subtracted a bit too much. So what we actually wanted to do was lower this down to some number like 0.5. And now you can see the green curve is actually kind of beautifully flat in that region. So we're getting, and I can expand that a little. So we want to concentrate on this region here. So here I was over subtracting the background, but now the background is flat. It looks like I'm still over subtracting even a little bit. So I can move this down a tad. It gets flat like this. And then what we can do is we can look at the PDF, and you can actually see that it has a very small effect on the PDF. Now it looks like I'm actually under subtracting a little bit because this goes up a tad. Now I want to move this guy down to 30 again. So now we get our nice low noise green curve here, and it's nice and flat. Now let's say that we're happy with that PDF. Let me play with one more thing here. So actually what's happened is that we've got data, we're using a Qmax inst of 30, but we've got a Qmax also close to 30. So I can show you what happens if you reduce Qmax. So what will happen is that it's happening in real time, so watch the G/R curve down below. Can you see small changes happening? So as we get down to a very low Qmax, it's probably easier if I blow this up a bit. Now we've got a very low Qmax. The peaks, the green peaks are lower. Actually, they're not. They have the same intensity, but they're broader. So lowering the Qmax has broadened the peaks. So that means that we're getting less resolution. But you can see that this was a Qmax of actually 12 or 13, 14. It's a Qmax of 14. And the green curve is quite acceptable PDF for some simple material like nickel. So you can actually get very good PDFs even for moly data. And if you look up here in the high R region, the effects are even less because the peaks are actually broader there. So the Qmax, the needing high Qmax is a little bit overstated, I think, often. But let's go back to this low R region. Now you can see the green ripples are becoming quite large. These are the termination ripples. And if we now go something very drastic, we can see that all kinds of things happen that are not very pleasant. So this is a Qmax of 6. So the green curve is a Qmax of 6, and the blue curve is a Qmax of 30. So if you did a copper K alpha radiation experiment, and you measured to, I don't know, to 90 or 100 degrees in 2 theta, you would have a Qmax of 6, and you would get that green curve. And basically the green curve doesn't look anything like the blue curve. And so that's why really copper K alpha radiation is not sufficient. If you do copper K alpha and you go all the way to 8, that's if you had a detector that goes all the way to 180 degrees. It looks like this. It's starting to kind of look okay, very broad. If you have a moly tube and you measure to high angle, you can get to about 12. So the moly tube would give you the PDF that looks like this. It's starting to look actually very good. If you had a silver tube, you could measure to 15. And it's starting to look really quite good. Okay, so usually my recommendation if you're going to build a source in your lab is to build it with moly. Anyway, let's say that we've got really beautiful data here, so we'll put the Qmax up to like 28, and look at how flat that green curve is. So that, I mean, the baseline of the green curve, that means that we've got a very high Qmax, so we've got no termination ripples, but we have very low noise. So that green curve is really a beautiful PDF. It's more beautiful than the blue one, in my view. So I'm very happy. So what I do is I type here, I'm happy with my config, so I want to save it. So I type process files and give it this paren because it's a function. So in Python, whenever you put the parens there, that means you're executing a function or a method. So I process that, and it tells me it's going to write a nickel.fq and a nickel.gr file, but it's telling me actually it already exists it won't overwrite it. So actually the program's very friendly. It tries to prevent you making mistakes. But we actually want it to write. So as an argument in this file, we're going to do force equals true. And we're forcing it to overwrite the file that's already there. We could also change the name of the output file, and I don't remember how to do that. In here, it's probably one of the config. It's probably config dot. So if you do config dot and then you press tab, you can see everything that's available. And we'd be looking for something like file name. So I'm not sure if it's there. But anyway, it's in the documentation. You guys are awesome teams. You can solve that. Okay? Now we can exit, and we have this G of R file. Now, this is two that we created previously, so you can compare yours against these. But this is the nice one that we made. So we could then use our plot data, nickel.g of R, and we can see there it is, beautiful G of R file, and we could load that into PDF GUI. We could do modeling. You can load it into Origin. You can publish a paper and become rich and famous. Okay, any questions? Yeah.
What is the meaning of our polynomial 0.9 and the round scale is 1
You're asking about R poly?
Our polynomial is 0.9.
Yeah, okay. So that's the one thing that I didn't go through. What's wrong here? Oh, I'm in plot data. I'm not in PDF. Okay, so our poly is the order of the polynomial that we're going to fit to the data before we subtract it. And the key with our poly is that we want to have that number large enough that we can fit all of the background, but small enough that we're not fitting any of the signal and subtracting it. And the basic idea is the units we gave for that is actually angstroms. And what you do is you look at your data and you see where the first peak is. So the first peak is here in the G of R. It's at about 2.5. And so in actuality, I can set R poly to any value up to about 2.3, 2.4. And I won't be removing any intensity from any signal from the data. I mean, strictly speaking, I should kind of look at this edge of the peak. So 2.2. So as long as I don't set our poly to any number greater than 2.2, I'm safe. So that's my safety thing. Now the R poly is set to 0.9. And what you can see is if I lower it, I'm lowering the order of the polynomial fit, like this. And if you look at the f of q function, you can see that it's actually not doing a good job of making it flat. So there's some kind of oscillation in the f of q function. These data are so good, it's actually hard to show it going bad. I've got barium titanate data that show it better. And then you end up having kind of noisy PDF. If you, now watch this peak here, and I'm going to increase our poly. So firstly, I can flatten out the PDF, and I actually flatten out my low R. So this thing is flattening out nicely as my PDF flattens out, as I increase our poly. And this is where we had it set by default. And if we start increasing it, we're now increasing it where we're a little bit overdoing it. We're giving it a bit too much to do. We're giving it too much freedom to fit the ripples in the data, and it's producing this like flat line here instead of a nice sloping line. Usually we don't worry too much about that. And we can take it up to 2 here, and now it's basically going very flat here, and then you're getting this ripple there. So this parameter is actually important if you have a low Q max, because you can really overdo things. So what we can do is we'll move this back to 0.9. We'll move Q max down to let's say 8. And now we'll increase this R poly. Okay, even then it's too much. The nice thing is that the PDF is quite robust. I mean, you can do fairly bad things with these numbers and still survive. But if we have a Qmax of like 6.5, so the R poly has a big effect. It actually moves peaks around now. So normally the R poly only affects this region down below the first peak that we don't care about. But later on it starts to affect peaks that are higher up. Okay, I'm having trouble showing it. So the recommendation there is you kind of leave it at the default value, but if you have a lot of noise in that low R region, you can gently increase it, but don't increase it beyond the first peak, the position of the first peak. Is good? Okay. What's the status with T and things like that? So they're ready. Yeah, so good. So I think it's T, and then you guys have to be awesome teams after T. T then teams.
Will we wait for T or we can?
Config, CFG means config, so you could just do
is overwriting our configuration file and demo. It is overwriting our file which is on the demo.
Changes we made.
Yeah, that previously or every time when we go for the run of the same material, we need to put it in some different folder. We don't need to put in the same folder. Otherwise, it will overwrite all the files of your file. It will only make changes in this file. This is the one. Over here, all the commands are in the past. यहाँ पर सारी commands दे रहे हैं, तो फिर changes वहाँ पे हो रहे हैं.
To take raw data and get a PDF, and the next stage after that is modeling. And rather than leave you to finish up GetX3 and do this tomorrow, I wanted to give you the PDF Gui introduction right now. There's not much time to work on it, but I'll show you how to use PDF Gui. You'll have a little bit of time to work on it, and you can actually then start actually fitting the data that you processed. And this afternoon, when you have access to the internet, you can download more tutorial examples for PDF GetX3, so you can play more with PDF GetX3. It turns out that the nickel example I gave you is exceptionally simple. It's almost impossible to get a bad PDF from nickel. If you look on the tutorial examples on the web, there's some more challenging examples. Cerium oxide, barium titanate, there's an organic material which is the most challenging. And what you'll find is actually you thought you were confident about PDF GetX3 because you could get nickel. You'll find that there are more problems, but the good news is I'm still here for 2 more days. So I definitely recommend that you try and especially work in your teams. It's much easier for me to help groups of people than to help individuals. So try and work in your teams and play with these other examples and have problems, and then I'll make myself available to try and help you. But at the same time, if I give you this introduction to PDF GUI modeling, you can also start playing with PDF GUI. And again, there's still 2 days, and we'll have more hands-on sessions during the other days, so don't worry, we'll have more hands-on sessions to work on these things, but I just wanted to start PDF GUI now so that you could start playing with it, okay? So the PDF GUI is for modeling. We've obtained a PDF from data, now we want to model it. Now, we went through this yesterday or whenever it was. So this is the basic layout. And if you remember, you have these different panels, you create fits, and what you highlight here, what appears here, depends on what you highlight. And this is about as far as we got, which was to obtain a structure, and then we highlighted the structure and we plotted it, and you could see the structure, and we did a calculation so you could see the PDF that was calculated. So the 3 steps are: you can create the structure, you can calculate the PDF from the structure, and the last step is we want to refine our structural model. So the basic idea is that the structural model that we have has parameters that describe it. So this is nickel, and one of the parameters is the A lattice parameter, and it has a value 3.52. And another one is the B lattice parameter, and it's cubic, so it has the same value. It has a C lattice parameter. It has X, Y, Z coordinate in the unit cell. It has an ADP, atomic displacement parameter. That's the amplitude of thermal motion of the atom. So this number will be larger if the atom is moving a lot. This number will be smaller if it's moving a little. And we have actually the possibility to do anisotropic ADPs. So if the atom is moving a lot in one direction, but not moving much in the other direction, then we have mathematically a way to model it. And this parameter is the occupancy. So sometimes on a particular atomic site, it's supposed to be silicon there, but there's only 0.8 occupancy. It means that there's 20% of silicon sites are empty. So we're able to refine occupancy. So you're going to actually do a refinement where what you want the program to do is to take all of these parameters, or actually not all of them, some of them, and you want the program to adjust those parameters in such a way as to get a very good fit, a good agreement between the calculated PDF and the model. So it's a way that the software program discovers for you what the right structural parameters are. So there's a key concept that we have to get into our heads here, and that's the difference between a parameter and a variable. So the parameters are things that describe the model. The A lattice parameter, the alpha parameter, which is the angle between the B and the C axis, the scale factor, the X coordinate of the first nickel. These are parameters. When we do the regression, that's what we call it when the model is trying to fit the data. What the model does is it takes some things and it varies them, and it varies them in such a way until you get a good agreement. Now, people get muddled up because actually what the mathematical function takes is it takes parameters and it varies them. So people don't know the difference between a parameter and a variable. But the parameter is what describes the model, and the variable is what the regression engine varies. So a particular example here is that this is nickel and it's cubic. So in a cubic material, we know that A, B, and C have to all be equal to each other. Now, right now, A, B, and C are all equal to each other, so I've made the structure cubic by simply typing the same number into each of these boxes. But when I start to do the regression, when I start the fitting program running, in principle it could change these numbers so they're not the same as each other anymore. Then actually what happened is that the fitting program made my structure not cubic. But I want my fitting program to keep the structure as cubic. So what I do is I make one variable. And what I do is I tie each of these parameters to that variable. And then the program varies that one variable, but when it calculates the PDF, it takes that variable, it unpacks the different parameters from it, and it varies those parameters. So that's the difference between a parameter and a variable. So is that clear? Does anyone have questions about that? Now, we have these three tabs here. The Configure tab, we've got the structure highlighted, and the Configure tab showing us all the structural parameters. So in the Configure tab, I put values for all of my structural parameters. If I click on the Constraint tab, okay, this is another Configure tab. Now I've highlighted the structure, and again, these are parameters. The fit range from minimum to maximum, Qmax, Qdamp. So these are model parameters that relate to the data. Now I go to the Constraints tab. So the Constraints tab, if I go back to the Configure tab, I have a bunch of parameters. And some of these parameters I want to fix. So the fit range, I don't refine the fit range. I want to fix the fit range. But there are some things on here like scale factor, Qdamp, Qbroad, Qmax I want to fix. Temperature and doping we're not going to talk about yet, but these are not refinable. So the only parameters in here that I might want to vary are the scale factor, Qmax, and Qdamp and Qbroad. So if I click over to the Constraint tab, it has scale factor, Qdamp, and Qbroad. Oh, did I say Qmax? Qmax is not one. So these are parameters here. Now this @ sign is a number that I type in, and this is a variable. So what's happening here is I'm saying I want to create a variable number 1. To specify that it's a variable, I give it this @ sign. So I type @1 into there. That's saying I've created a variable, I've given it the name 1. And because I typed it into that scale factor box, it means that the scale factor of the data set is going to be associated with that variable. Now there's this other parameter that I'll talk about a little later called Qdamp, and we're making that @2. Now these numbers here, they're just names. They have to be unique. Like if I create another variable called @1 somewhere else, then what I've done is I've inadvertently imposed a constraint because I've put 2 different parameters to the same variable. So you have to be very careful how you name these, but you don't have to do it sequentially. And the advice I would give you is that parameters, again, you don't want this accidental thing of 2 parameters, 2 variables being associated, 2 parameters being associated with the same variable. So we tend to separate them by kind of orders of magnitude or something like that. So these parameters I might call 1 and 2 and 3, but on a different pane. This is the structure pane now. So what I've done is I've highlighted the structure. I've clicked on the constraint pane. And here, actually, I've called it @3. So I've associated A lattice parameter with variable 3, B lattice parameter with variable 3, and C lattice parameter with variable 3. So in order to ensure the thing is cubic, I've made these guys to be all the same variable. What might I do if I wanted to make it tetragonal? Does anyone know? Yeah, so tetragonal means A and B are the same, but they're not the same as C. So what I would do is I would make these 2 to have the same variable number and this one to have a different variable number. And that would allow the program to independently vary. So it would tie A and B together, but it would independently vary C. So you start to get the idea.
Also 2 or 1 here in the structure constraints.
Yeah.
Instead of @3,
Yeah.
we have @1 or
Yeah, so that's a big danger because at 1, we created a variable called 1. And we associated actually the data scale factor with that. So if I use at 1 again here, then I'm actually inadvertently tying together the data scale factor with the lattice parameter. So even though this variable is on a different pane, it has to be, it's kind of global, it's a global parameter, right? So I can't, once I've used at 1, I can't use it again. So now I've set up my refinement, and I click on my fit. So I select fit, and all of the, unfortunately, I couldn't convince my guys that developed the program to call these variables, so they call it parameter, but this should actually be variables. But here are my variables that I created. Remember, I had at 1, at 2, at 3, at 4. So this is an unfortunate example because these are all just sequential. I don't like to do it that way myself. But these are the initial values of those variables. And here's plot control. I don't know why that's highlighted. But basically, I have this selected. I press. This thing says fixed. So this is not checked for any of them. So it means that each of these variables is going to be refined. The program can change each of these variables. And I have this selected, and I press that button there, which is it's like a cogwheel. It's supposed to indicate that the program is working. Now, something that you should do first before you do anything is you should go back to this configuration page for the data, and you should make sure that the fit range is narrow. I would advocate putting something like 0 to 10 initially. Otherwise, the calculation can take a long time. So while you're making sure your model is correct, you would set it from 0 to 10. Then when you're close to having a good solution, you can then change that R range. So we hit the cog button and the thing runs. Now this pane down here, this is actually the output from the program. So we haven't hit the cog button yet, so there's no output. But we hit the cog button and suddenly some output appears. And if you can scroll up and down and you can see all of the output. This is just the bottom line of the output. And it's showing you actually how good the agreement was. And this RW is one that we use a lot. And a good fit is something around less than 0.2. And a very good fit is around 0.05. So 0.09 is quite a good fit. Why is there such a big range? It depends on the quality of the data and the quality of the model. So when we're fitting nickel, we have very good data, we have a very good model, and we can get, actually we're getting down to 2%, so 0.02 for our RWs for nickel. But if you have a nanoparticle and it's got a bunch of disorder in it, and it's got some organic ligands that are not in your model, and there's all kinds of stuff going on, 0.2 in that case is still quite a good fit. You just have to play with the program to get some feeling for what's a good fit and what's not a good fit. Now, as well as once this thing is finished and converged, then what you'll see in this parameters pane is actually the refined values. So you can see the variable number 1 was at 1. That was the scale factor on the data. It had an initial value of 1. But after the refinement, we found out that actually a better fit was obtained if we scaled the data by 0.76. Right? So this is the final refined value. And these are the refined values of these other things. Now, what we often do is we often want to make the refinement go sequentially. So we want to turn on one parameter, refine it, make sure everything's correct, turn on a few more parameters, make sure they're correct. And what we want to do is we want to use as a starting point for each subsequent for each step, we want to use as a starting point the best fit we got from the previous point. So what you do is you basically right-click on here, and you get this thing here. It says copy refined to initial, and if you select that, it will take these numbers and it will put them here. I'll show you in a sec. We have plotting here so you can actually see what's going on. There's other kinds of plots you can do. This is actually showing how the RW, so the agreement, varied as a function of refinement step. So actually the way the software works is it computes the PDF, it sees how good the agreement is, it decides how to change the parameters, it changes the parameters, it recomputes the PDF, it sees how good the agreement is, it decides how to change the parameters, it changes the parameters, it recomputes the PDF. So it's a kind of a sequential process. And the idea is it's coming downhill. It's making RW come downhill until the RW converges. And this is just following that. It's not super rich in information, but you can do it.
It should go down then.
Huh?
The RW should fall.
Yeah.
It should not go up.
It should not. So RW as a function of refinement step will go down. But we often use RW as a measure of how good the fit is. And so we often plot RW as a function of temperature. So we have 100 data sets all taken at different temperatures. And then we plot RW versus temperature. And you see all kinds of things. It comes down, it goes up, it goes down. When it comes down and goes up, it means you've had a structural phase transition, because the model was working well, and then suddenly the model's working badly. So it's a very powerful way to investigate your data. This is showing that you can actually put notes into this, and I don't even know how you do that. I never used that function. But I just learned that from this view graph. This one I think I'm going to show you in person. It's easier. Oh, well, we talked about that space group expansion actually yesterday, or whenever it was. And this is more advanced usage, so we'll come back to this. So I'm going to actually do a real-time demo so you can see it working. Now, there's one thing that's not shown here, which is extremely important, and that is that actually sometimes PDF GUI crashes. And if it crashes, all of your work is gone. But you can actually save the current state of your work in a project file. So if you go to File and you click on File, you get a drop-down list. One of your things is Save Project. And what you want to do is you want to pick a name. You guys are all good at picking names now. So you pick a name and you save it, and it has a file extension DDP. And it contains a complete state of your refinement at that point. And what's actually useful is you can use that for archival purposes. So, when you have the refinement that you're going to publish in a paper, you might want to save a project file, and you give it a name like nickel refinement _ published .ddp. You don't have to say .ddp. You just call it nickel _ published, because then you can go back later, and that's exactly. But you can also save intermediate versions. So you can say nickel _ happy with this version .ddp. That means you think you want to publish that version, but you actually want to play around with some more things. So you go and you play around with some more things, and everything gets worse and it goes horrible, and you're like, oh, that didn't work, but now I've ruined my input parameters. I can't get a fit at all. My program is not working well. But you saved that intermediate version with that name, so you can go back and you can open that one, and you're back to where you were when you saved it. So the basic advice is save frequently and often. So you save as with a new name when you want an archival version, but you can just do Control S, Control S, Control S once you've saved a project file once and you do Control S, it's just going to update the same file name. Okay? Questions? Yeah. Yeah. Yeah, so very good question. So there's a scale factor in the data section and there's a scale factor in the phase section. So in actual fact, they're redundant. You mustn't vary both at the same time because the program, those two parameters will be highly correlated, and the program won't know how to vary them. But the reason that you need a scale factor in the phase is that if you have a multi-phase system, so you have a mixture of silicon and nickel, that's one of the examples, and you have 25% silicon and 75% nickel. You want to do a two-phase fit which has a silicon model and a nickel model, but you want the scale factor for the silicon model and the nickel model to be different. Right, so you actually, what you do is you in that case you make as variables those two parameters. I'll probably show an example one of the subsequent days. In that case you would set the scale factor for the data to 1 and you would fix it. On the other hand, we think that there's a scale factor for the data itself. So if you wanted to fit a model but you wanted to extract an overall scale factor which is telling you how well your data were normalized, you could fit the sample data. But my recommendation is that in the sample scale factor you set it to 1 and you don't vary it. Okay, so here's my PDF GUI. I just started it and it's running. And if you remember rightly, the first thing I have to do is I create a fit and I give it some name. Nickel example. There's my nickel example. I want to, let's add some data first. So new data set. So let's see, do I have a nice nickel PDF? So I have a nice nickel PDF here that came from my PDF GetX3 tutorial. Let's try that. And let's just plot it to make sure it looks good. Firstly, the fit range here is up to 60, so let's just put this, before I get into trouble, let's put it down to 10. Now I'm going to plot it. So it looks like a good PDF. We're going to try and fit this PDF. So now I'm going to add a phase. And I'm going to create it from scratch. And it's going to be nickel. So again, you go back into that file directory. You can either go to the web to find good parameters from a structure file, but it should be in the README file. And we know that it's 3.52. And I'm going to go a little bit quickly because I want you to then try and do it yourselves. I can leave the scale factor here like this. I want to include an element. So I want to right click, insert atoms. I want one row, and I'm going to make it to be nickel. Now I have to expand this. So I want to expand the space group, and it was FM 3 M. So hopefully it worked this time. So sanity check. I can plot my structure. Yeah, that's correct, right? So that's good. So another sanity check. Going to do a sanity check calculation. I'll run it. and then I'll plot it. So that's what it plotted to. So despite our difficulties yesterday, it went more smoothly today. So this is all what I did yesterday. There's the data, there's the model, and it's looking pretty good. So I want to do my first fit then. So to do my first fit, what I have to do is I have to set up these variables. So the first one that is actually good to do is actually set up, just do a scale factor, let's say. So we'll make a scale factor. Here's my scale factor in this structure. So I want to make a variable, and I'm going to call my scale factor at 1. And now if I go to my fit, I've got one variable called at 1. It doesn't tell me here it's called scale factor because it only knows it's a variable. It doesn't know what parameters it's associated with. And now I can click on this. I'm only fitting up to 10. So it's gone quickly. It's already finished, and it's 0.2. Now if I click on this guy, this is my fit. So you can see it's going pretty well. It's actually, the peaks are all in the right place. So my model is in good shape. But it's getting a bunch of things kind of wrong. So what I want to do is then I want to say, okay, what can I vary now? So lattice parameter is probably the next thing. I need to shift the peaks. Actually, it's going to be actually pretty close, but you can see that they're a little bit, they're maybe possibly a little bit shifted, not by much actually. So remember the difference between the configure. So if I go to the configure pane, I have values in here for my parameters. If I go to the constraints pane, I don't have any variables set. But I want to set, so I'm going to call these, I think everything on this page I'm going to start with at the 10 level. So I'm going to call it at 10. And then because it's cubic, I want this one to be at 10 and this one to be at 10. So now I can go back here, and now I have two parameters. Now this one here, I might want to copy it over to there, so I can do it in two ways. I can double click on here, and I can go 0.3 and use that as a starting parameter. I can also do this copy refined to initial, and I could use that big long number as a starting parameter. And now I click on this, it runs, and I can click on this and click on this, and so that's my fit. All right, what should I vary next? So you can look at the fit, and the peaks are in the right place. Roughly speaking, the amplitude is quite right, but it looks to me like actually the peaks are too narrow. If I look very carefully, it looks like my red curve is to the right of the blue dots here and to the left of the blue dots there. And in the difference curve, I get this M-shaped thing. That's very characteristic that my fit peak is sharper than my real peak. So the way that I can vary the sharpness of my peaks is by varying the ADPs, and that's a model, that's a characteristic of the model. So I go here, and so it's what I want to do is vary U11, U22, U33. Now I could give different variables to all of these. It doesn't, all of the nickels are equivalent to each other, so it doesn't make any sense to give different variables to different nickels. But it might make sense to give different variables in different directions. U11 is the X direction, U22 is the Y direction, U33 is the Z direction. But it's a highly symmetric structure, and you should always start with the most simple model. So what I want to do is I want to create a variable, and I'm going to call it at 11, and I associate the same variable with all of these guys. Now, it's actually important to make sure that these initial values are all the same. So these are all the same. So when I apply this constraint here, I can make the constraints all the same. Everything will work fine. So now I click up here. Now I'm not actually going to bother to move this over because these numbers are so close. So I'll just run it. And now it went from, it was 0.26 or something, it went down to 0.11. So we're making really great progress. I know that it's going to actually look much better. So now I've got actually a good model. I've got a good starting place. Before I do anything else, so what I say to my students is I say, you know, whenever you're in a happy place, save your file. I'm in a happy place. I'm going to save my file. So what I do is I say save project. I can do save project as, but since I haven't already saved it at all, it's going to ask me. So now I need a project name. So I'm going to call it live demo. A live demo intermediate, let's say. So it's saved. So now I can say, oh no, I accidentally closed PDF GUI. It's a disaster. But actually it's not a disaster because I just have to run it again. And here it is, and there's nothing in it. But I can go to Open Project. Now I do have to navigate to it, so there's a little bit of work. I have to remember where it was. Tutorials. Actually, I don't remember where it was, which is a bit of a problem. But I think it was in PDF GetX3, was it? Oh no, we're in big trouble. I don't remember where I put it. Oh, there it is. Live demo intermediate. Yeah, praise to the gods. I got lucky. So the second rule of programming is never give live demos. So now we can look back where we were, and here it is, our beautiful fit that we're very happy with. All right, so I'm in my happy place. I've saved my file. Now I can continue. I don't think I need to save an archival version with a different name. I'm just going to keep going. So actually what I want to do now is I want to, because I've got a good model, let's extend the range that I'm fitting over. This will make it go more slowly, but I'll learn more. So 20. And now let's go here. Do we want to? Yeah, let's do this thing of right-click, copy refine to initial. Then we'll click that guy. So now something terrible has happened. Our RW has gone really bad again, 0.2. So let's see what happened. We click on the data. We click the plot button. So now actually we have much more information in our model, but it's fitting kind of well in the middle, but it's not fitting out here and it's not fitting down here. So we actually need to refine QDamp. So you need to gain a little bit of intuition with the program to know what to fit. But basically what's happening, this is my characteristic W or M. This means that the data are sharper than the model. And out here, the model is sharper than the data. And the amplitude of the model is too high here. So the peak to valley of the model is higher than the peak to valley of the data. And the peak to valley of the model is too low down here. And the peak to valley of the model, this region in the middle, is fitting perfectly. So what it actually means is that there's a Q-dependent intensity problem. Like my model has a fall off in Q, not in Q, and my model has a fall off in R, and the data has a fall off in R, and those two fall offs are not happening at the same time. This is actually, because nickel is a bulk, this can be two reasons. One is that you've got a nano-sized material, we talked about that. But nickel is not a nano-sized material, nickel is a bulk material. This is actually coming from the resolution of our instrument. and the parameter that controls that is QDamp. Now that's a characteristic of the data, not of the model. So I want to click on the data, and then I want to see, okay, I have a QDamp of 0.001. I think, well, let's see if it works. And I want to set my QDamp. So all of my structural parameters I had as kind of at 10, 11, 12. All of my non-structural ones I want down 1, 2, 3. So I'm going to call this one at 2. And I'm pretty sure that I don't have at 2 set. Let me check. So I can go here. Yeah, there's no 2 here. So 2 is available. So I can go here, and my QDamp is going to be at 2. And now set this thing to go. Now, here's an interesting thing that happened, and people get very stuck with this. It refined and it converged, but this RW didn't change much. So these were the initial values, these are the refined values, and they're actually kind of the same. So the program actually got stuck. And when this happens, it's usually because there's a matrix inversion, and actually the matrix inversion was unstable. And the reason is actually this value is too small. So the program, what the program did is it tried to change that value by a small amount, but because the value was too small initially, the small change was so small that it didn't produce any change, and then the program didn't know what to do. So we can actually unstick it. This is something about numerics and numerical stability. It's a mathematics thing. But we could do 0.05. So we'll set that guy to 0.05, and then we'll try again. And now it's working. So now we went from RW of 0.2 down to 0.11, and these numbers here, they all changed a bit. And we can plot this guy. It's starting to look actually very satisfactory now. Things are looking good. I'm definitely I'm in a happy place. What should I do? I forgot. Oh yes, save. So I can do Control S, or I could go File. Well, I can't do Save Project because I just saved it. So I've saved it, so now the program can crash and I can recover. But I want to do one more thing. So let's look at this again. You don't need both of these. So things are like reasonably okay out here. This thing is going to need maybe a little bit of work later. But the low R peaks, a very interesting thing is happening, that the data peak is sharper than the model peak. This is actually a real physical effect. It's coming from correlated motion of the atoms. So atoms that are close together in the material, remember this is a pair distribution function. It's showing the distribution of lengths between pairs of atoms. So imagine that there are two atoms in the solid and they're separated by some distance, but there's a strong bond between them, a covalent bond. If the atom on the left moves to the right, so if it tries to move this way, it's strongly bonded to its neighbor, so it actually pushes the other atom over. So these atoms can be actually undergoing large amplitude motion, but because they're directly bonded to each other, the PDF peak will be very, very sharp, because when this one moves to the right, the other one moves to the right. It's correlated, the motion. So what actually tends to happen, okay, imagine then you've got the second neighbor. So if these guys were connected by a metal rod, they would move exactly together. And then that's connected to another neighbor. Then the second neighbor would move exactly together, and the third neighbor would move exactly together. But the atoms are not connected by a metal rod, they're connected by a spring. So you can imagine it like this. Let's say it's a very stiff spring. One way to imagine it is that you've got a metal rod, and you cut the metal rod and you put a piece of rubber in, and you do that for all your bonds, what happens is that these guys, they still move together because the metal rod is there, but they don't move perfectly together. There's a little bit of wiggle. The second neighbor, the same thing, but there's now 2 bits of rubber. So they're decorrelated a little bit more. The third neighbor, there's 3 bits of rubber. And now the motion is becoming quite uncorrelated. And what happens is in the highest neighbors, the motion is completely uncorrelated. So when this one is moving to the right, this one could be moving to the left or the right or anywhere. This guy has no knowledge of the direction that this guy was moving in. That's uncorrelated motion. And so what you can see is that as a function of R, the motion is more correlated and it becomes less correlated. So we have some parameters in PDF GUI which account for that, and what they do is they sharpen the low R peaks. So the 2 that we like to use, and we don't use them both at the same time, are delta 1 and delta 2. So you need to go and read the manual to see exactly what the functional form is. But delta 1 is a like 1 minus 1 over R variation, and delta 2 is 1 minus 1 over R squared. So the delta 2 is a sharper one. So I don't know which one is going to work best, but we can just try. So we want to give this delta 1 an initial value, so we'll give it, I don't know what good values are, so we'll give it like 0.4 or something. And then we want to create a constraint for the delta 1. And we've used at 10 and at 11, so let's use at 12. Actually, that delta 1, it's kind of not really part of my structural model. So I think I'm going to give it at 4. And let's see if this can help. Okay, so it has helped because RW has gone down to 0.08. And if I plot this guy, now we're getting actually really quite a good agreement. This part down here you don't want to worry about because this is unphysical, and you know that in PDF get X3 you can kind of vary this region by varying R poly or some arbitrary thing. So we're not worried about the misfit there. So we can actually improve our RW and get rid of this contribution by setting the R min to some value here, which is this guy is 2.5. So let's set R min to 1.8. So that's a well, let's just do 1.5. So now we're down to 0.07. Let's copy refine to initial. I'm in a happy place. Let's save. And let's plot it. So it didn't actually change the fit, but now this part is not contributing to the RW. And then after this, we can go and play with a few other things. I think that we might need a Q broad here. So I don't know what value that should have. So at 1, 2, 3, 4, I think we're up to 5. Let's check. 1, 2, 4. Oh, there's no 3, so I didn't use 3. So let's use 3. Click on this, click on this. RW is now down to 0.48. So that's a good fit right there. So what I would probably do there is I would say, firstly I would save it, but then I would also save as, live demo. Final version. Nickel. Save. And we're done. If we wanted to, we could look at the structure. I mean, it's not going to look any different than it looked before. But if you allowed atoms to move around, it would look different. Okay, so we already ran out of time. Damn. Yeah. So what I wanted was for you guys to just try it real quick. But I don't know if they can try it or whether we should.
How to get this sanity check?
This is so I called it that, but it's just a calculation. So this guy is calculations. So you just say calculation, new calculation. I can say Atol's sanity. Should we call it that? Let's check your sanity. Oh yeah.
Okay.
Yeah. Any more questions?
I got a message, singular matrix.
Yeah. Singular matrix means it can be a number of things. It can be an unstable refinement. It basically means that if, for example, you might get a singular matrix if you have a cubic material, but you set up A and B and C to be different. And then that will produce a singular matrix. But the most common one is that you have some value set to 0 as the initial parameter. So you should always try and worry about that. Like if your ADPs had an initial value 0, you might generate a singular matrix error. So usually you can go back in and you can dig around and you can find some input parameter which is producing that instability.
What are ADPs?
ADPs are atomic displacement parameters, which is the crystallographer's way of saying thermal parameters. It's a measure of the amplitude of motion of the atoms.
Are they same as Debye-Waller factor?
They're the same as Debye-Waller factors, yeah. Yep. So I think, oh yeah, question. Yeah, so there's a theoretical basis for that. It's coming from the correlated Debye model. So at low temperature, the asymptotic behavior in the correlated Debye model gives the 1 over r squared dependence, and at high temperature it gives the 1 over r. So that's the long and pompous result answer. But the correlated Debye model is too simple of a model for most systems. So what we do is we just use them like parameters, and you try one and see how well it does, and then you turn it off and you try the other one and you see how well it does, and you use the one that works best.
You go to your homes and practice. They will learn.
Yeah, so we'll have tomorrow there'll be some lectures, but they'll be hands-on, and I've made the demonstration, but we'll do hands-on. And tomorrow, if we can get a better list of names, I'd like to remake the groups. So you're working even with different people.